Okay, so I want to emphasize I didn't give you what these coefficients are, but you looked them up in tables. But the Prandtl assumption, if it was a 1/7 power law, the coefficient of friction is 0.027 Reynolds number to the same power law. Again, you should know that those are going to match. Okay. But that was, that's a very old assumption on what that velocity profile looked like. We know that one of the better ones is this log law of what the velocity profiles looks like, where you have to remember that these kappa and beta are really the experimental fit constants. We know for a fact that B is basically always 5 for nice and turbulent, and this kappa is always 0.41. We find that pretty consistently. And then there's also this skin or friction velocity term that we non-dimensionalize velocities by. So it's people do fight a lot because before we always non-dimensionalized by the external flow velocity, but in this idea of turbulent boundary layers, right? Now we say to non-dimensionalize by this skin friction velocity. And then there's another layer, let's say, above, where then you start dimensionalizing by. This is all like way too much, but that's hard. That's a hard concept of what do I non-dimensionalize by? This friction velocity, or I still non-dimensionalize by the external flow velocity? In turbulence, that's not a easy question, and people go with this. But if you go about the same steps with this, just like how you could derive the Kolbe equation, right? You would do all those same simple methods with the 1/7 power law. And then you would get this. Really, you could only get power law relationships with this, and there'd be, but you're using this and then adding other extra fitting parameters. You get to the friction coefficient, and this is for smooth. So you're already experts, I think, and that's why this is a short lecture on this idea of smooth surfaces, rough surfaces, fully rough surfaces, turbulent versus laminar. So I'm just writing another Moody diagram for you with other equations that you need to plug in to get the value you're looking for. So I'll just write it out again. This is a short lecture, because really that last one you could maybe watch a bunch of times and ask me a lot of questions on why I'm not making sense. Trying to make sense, I promise. So then you get other relationships. Where this is for fully rough or for very large values of the roughness. Again, you use L, not the diameter. So before you use diameter to non-dimensionalize, this is the roughness height of the surface, and this is actually the length of the surface. So really what you're measuring are like the deviations, right? So that's why you non-dimensionalize. The roughness is sort of like the largest gap, not depth. That's for fully rough. Other turbulent one we get is same thing, but just this is transitional. Okay, and there are more in the textbook of where these equations are coming from. I have another one. I think I have one more. Not found. No, those are the ones. But there's a nice table in the textbook. I think I'll send that out as well of just all these different ones. With those functions, you can just calculate another Moody chart that would correspond to your external flows. So you can even use the same chart, but the idea is you're trying to calculate that C of F always. So that is half of the drag story. It's half of the drag story because remember that we're always... That was really fast for the turbulent boundary layer, but right, you really could take a whole class on the turbulent boundary layer. It has many layers. If you're super interested about turbulence, your professor by Cal in our department, he's the major guy. He does turbulent boundary layers. There are a lot of assumptions that go in, but at this level, I think it's easiest to understand that by just make some assumption of what this is, the non-dimensional one, and then do that process. Right. Right. Make this assumption and then plug it into there. Right. Another way, so you have to make this one, and you actually have to make this one as well. But it's always going to be some relationship like that. Usually not anything else, but that's really right. So that's, I think for turbulence, I think it's just okay to understand at this level in these classes that you make assumptions, and we know intuitively that for nice laminar, it has this 1/2 relationship of growing. So it changes along a plate, and then for the laminar case, it has all these negative 1/2 relationships to the Reynolds. And for turbulence, it's just okay to understand that I know it just gets sharper, right? I think that's totally fair. That sort of looks like this, where now there's kind of really low. There's a sharp region. And then over here, sort of a slow growth to the infinite velocity. So it's just kind of sparsing down. We get that too because, right, you have this, right, as that Reynolds number increases, I know the boundary layer decreases as well. It's flattening. And it gets so much that it just eventually gets turbulent. And then it's all approximations. Anyway, what I was saying is we've only answered half of the question. Because when it comes to drag, it's really a vector. Okay, so there's two components. This is for any body, right? So if I have some sort of body like this, it has a normal vector and a tangent vector at every point along the surface. This is the area, right? So I can kind of go along this way. So think of this as, this is y, this is x. You could think as n and t. If I could parameterize this as some sort of loop in xy space, so this is some curve. Let's say lambda. Right, you could parameterize it, and then these would be, right, vector calc-wise, this all makes sense. And then it's a pressure field and this tau field that we got before. So for flat plates, it's not that hard. I think the homework problem you have is a flat plate, but I didn't give an example of that because there's one in the book. I think it's okay to understand this skin friction part and pressure for a flat plate angled. So this is what we were calling skin friction. This is called form drag. Okay, so we kind of just did all the tools to get all the parts of the skin friction part, right? And this is tangential forces. So tangential forces are those sort of viscous So viscous friction forces are here, right? We need to use the boundary layer analysis. Boundary analysis, right? We care about these quantities. And then, right, the idea is it's a function. It's a function of Reynolds and this. So then up next, we need to talk about form drag, which is how the pressure changes over a body, right? For a flat plate, this goes away because everything's going to be perpendicular to the normal on it. But if it's curved, this is not true. So there's another component of drag force, which happens because of geometry. So this is about the geometry of the body. Right? This is a distribution of pressure over the body, which is changing because the streamlines have to change. So that's the last thing we'll do for external flow. Next lecture is go over this half of drag. You'll see this one is normally bigger than this one because it's just little viscous forces. But the almighty boundary layer, which I call it the almighty, it does have an effect, and a measurable effect, that there is a bunch of force you don't account for if you don't look at the viscous force on there. But we will see that this term is usually bigger. So before, I think people just use this term, not that one. I think we fly better because we understand that. I actually don't have any more. I have a little chart in my notes of a summary of all the constants and the things you calculate, right? So, right, in our travel, right, I kind of got this thing down, which is just sort of like friction factor. And we actually have it for the laminar and the turbulent. The turbulent I really glossed over, but it's just more equations that you can just make your own Moody chart for. I highly recommend doing that because you get a sense. So the next one is this coefficient we're trying to figure out, which is about the form drag. So we'll have the same definitions. There's now an equivalent to the internal flow because we just really had the one friction factor we had to worry about. But for the pressure, for external flows, there are two of these coefficients we are trying to calculate. Why are we trying to calculate them? Once again, always keep in your head this. This is, right, so this is definitely, think of it as energy requirement. Right? This is a design. It's a design requirement on that side. So that leaves this thing then, the drag force, for an engineer to leaves you an engineer to guesstimate this term right here. Then you can get your energy requirement based on your design requirement, and you know what you need to buy. So that is where we're, right, the idea, everything, if you're ever lost with these external flow calculations, keep that in your head. That they're very important because you won't know how powerful your jet engine needs to be if you couldn't actually estimate this. You certainly would waste a bunch of money if you just said it's big.